textbooks in North America are always very interestingly organized. For example, grade 6, we begin with problems, exponents, and algebra. This should hopefully be mostly review. So, problem-solving plans. Well, for any sort of problem, it's very useful to have some idea of how to approach a problem in terms of your general steps, like explore, in other words, actually read the thing and figure out what you're given and what is required. Plan, so you choose a strategy to solve the problem and make a guess at the answer, an educated guess, also known as an estimate. You solve the problem and then you check it. Now, there are other abbreviations such as GRASP, which is the one that they gave us in high school, which was given, required, analyze, solve, present. Checking comes after. Like GRASP is what you're given, so what you know. Required, what you're supposed to find. You analyze this, in other words, plan. You solve it, and you present it by like putting a statement. Like say, the question asks, how many hot dogs does whatever football team eat? If each person eats this many hot dogs and there are this many people, your present would be, the football team ate this many hot dogs, or can eat this many hot dogs. Like you would put a statement. And then, of course, you would check your answer. But for problem solving, yeah, we went with that. Here, we're going with EPSC, which is not as easy an acronym to pronounce. EPSC. Yeah, no, let's not do that. So it's explore, plan, solve, and check. Let's use this 4-step plan to solve this question. Explore. Explore. Well, we have 30 canoes. Canoes. $15 per day each. And how much for July, which has 31 days. Your plan would be for most of the questions we do presently, you only have separate plan and solve steps, really, if you don't actually have an idea of how to approach the problem initially. Like plan is you brainstorm. Well, then this would be 30 canoes times $15 per day per canoe. Technically speaking, this should be per day dot canoe, as in when you're dividing by both day and canoe in a sequence, you have a fraction that's dollars per day per canoe. But this is also okay for our purposes. And then times 31 days. Okay, so solving would just be evaluating, which is this equals, how do we do this? Oh, we can do it manually. 930 times 15, or yeah, okay, it's pretty obvious because I'm holding this. But this is equal to $13,950. So, check. So, is this reasonable? Oh, it's going to be approximately, well, it's going to be a little bit more than 450 times 30. Now, because it's times 31, you can also go with 450, 30 times 15 is 450, times 30 plus 450. So if you have 450 times 30, 450 times 3 is, oh, you have 900 and then you plus 450 again. So 13500 per times 30, and then you add 450. Oh, okay, this is correct. Check. 450 times 30 plus 1 is equal to 13,500 plus 450 equals 13,950. Yeah, so honestly, if you actually can just go through the problem right away, you don't necessarily even need to have an estimate in the plan stage. Use a 4-step plan to solve each problem. Colin works for his dad during summer vacation. His dad pays him $5.20 per hour, and he works 20 hours per week. How much would Colin earn during his 8-week summer vacation? Well, explore is $520 per hour, 20 hours per week, 8 weeks. Total dollars equals what? The plan is pretty simple. You multiply all these numbers, including their units, together, and you end up with hours canceling with hours, weeks canceling with weeks, and you end up with just dollars. Because this multiplied by this, the hours cancel out, and you end up with dollars per week. So 520 times 20 times 8, which is equal to, you know what? Yeah, let's do this. 5.2 times 160, that's $832. Yeah, this is plan and solve then. Check. So is this reasonable? Let's see. It's about $5, or it's a bit more than $5 per hour. 20 hours a week. 5 times 20 is 100, so it's going to be a bit more than $100 a week. And for 8 weeks, so it's going to be a bit more than $800. So 5 by 20 by 8 is equal to $800. So this looks about right. So looks reasonable. The reason why I'm doing the estimate approach of checking is because there is no way to check this problem without just redoing it all over again. Yeah. So really, you only need the full 4 steps if you're doing a problem that you are finding, well, problematic, so kind of difficult. For problems where once you list out all the things you're given, it's really obvious, well, there's a reason GRASP often just puts the analyze at the formula stage, and then solve is when you start substituting numbers. So just like here, the plan and solve can often merge together. So we got 33 books. If he puts away 9 books the first hour and then 6 books each hour after that, how long will it take him to shelve all 33 books? This is like saying he has to shelve 30 books and each hour he shelves 6. because it's 9 books in the first hour. If you cut that down to 6 books, and the other 3 were magically shelved, then you would have had 30 books to shelve. Like -3 here, -3 here. And then you could find 30 divided by 6, which leaves you as 5 hours. How else are we doing it? Expected. This is expected time is, well, we explore with 9 books. First hour, 6 per hour after. 33 total. Time equals what? Okay. Plan. We're looking at 33 minus 9 books after the first hour divided by 6 plus 1. So this is plan and solve, really. Equals 24 over 6 plus 1 equals 5 hours. Check. 30 books at 6 per hour equals 5 hours, which tells us that 33 books, if you increase the first hour's books shelved by 3 and the total number of books by 3, does that change the time? No, because the first hour canceled out the increase in the total. Okay, number 3. Alicia bought a $48 sweater on sale for $25 and a $36 purse on sale for $22. How much did she save? So explore. $48 to $25. And the third, as you can tell, I'm abbreviating a lot of writing. $36 to $22. Saved question mark dollars. How many dollars? Well, plan is pretty simple. We find the difference in the prices. So we're looking at 48 minus 25 plus 36 minus 22. Solve. That means this is equal to 48 minus 25. Well, we know 50 minus 25 is just 25. So 2 less than 50. Oh, that's going to be 23. Even if we didn't just long subtraction it in our heads, which is also doable. 36 minus 22. Well, 36 minus 20 is 16, and then minus 2 is 14. Okay, 14. So, you add these together and you get $37. You know, it's really interesting how the dollar symbol can come before or after, and there are actual arguments about the conventions. Except when you put it at the end of a problem, after an equal sign. There, I mean, in my experience, it's usually after, just like every other unit. Okay, checking. I don't see a way of checking this problem that does not consist of just redoing the problem itself. However, you could do, say, 48 plus 36 minus 25 minus 22, which is equal to 48 plus 36. Why am I doing this? Oh, we don't need to do that because these are multiples of 12. 7 times 12 is 84, and then minus 25 minus 22 is equal to 37. Yeah, checking can sometimes just be take out calculator, press buttons. A lot of these questions, checking pretty much consists of looking at either this is reasonable or not, or do it by a calculator. There aren't that many questions here that you can do by alternative methods, really. I mean, geometry problems, sometimes you can, but even then at this grade level, they aren't that common. Okay, so let's say it costs $3.73 to mail a package to somebody's grandmother. The post office charged $2.38 for the first pound and 45 cents for each additional pound. How many pounds did the package weigh? Oh, it's more like what range the package weighed in, because it's each additional pound rounding up. So explore. $2.38 for first pound. Pound. $0.45 per additional pound. Yeah, for some reason the abbreviation for pound is LB. I do believe this is like from French origins or something. Whatever. So, cost was? Cost $3.73. Weight equals, we don't know. Weight equals what? So, plan, pretty simple. $3.73 minus your first pound cost divided by 0.45, so cost per pound, is equal to the number of pounds beyond the first pound. Therefore, you got to add the first pound back in and solve. You just simplify. Of course, plan usually consists of a lot of text writing before you actually substitute the values in at the beginning of solve. But for a question like this, come on, we can keep track of everything, right? Also, it's kind of tedious for you to watch me write like a wall of text. So, 373 minus 238 is 1.35 over 0.45 and plus 1, which means we're looking at 3 plus 1, or 4. Actually, this means package was between, because it says per additional pound rounding up. That means like a 1.01 pound package, you charge the same fees as a 2-pound package. So, in theory. In practice, yeah, the post office workers probably wouldn't mind too terribly, because it could be just scale calibration error. So, stamp it, whatever. Okay, package weighed 3 to 4 pounds. Now, in terms of checking, it's probably 3 times 0.45, or precisely speaking, 4 minus 1 times 0.45, plus 2.38, and we would find that it equals 3.73. 3. So this confirms our answer. Checking, you can work backwards as one of the ways of checking. If you don't have an alternative way to work forwards, it's usually go back, go back. So here we have powers and exponents. The exponent tells you how many times a base is multiplied together, like 2 to the 3rd power. This is the exponent. or power. And the 2 here would be the base. 2 to the third power is 2 times 2 times 2. So there are 3 2's. 2's here. And it's equal to 8. Now let's do some examples. Write 6 to the third power as a product of the same factor. Well, 6 to the third power is equal to 6 times 6 times 6. Evaluate 3 to the fourth power. 3 to the fourth power is equal to 3 times 3 times 3 times 3. Or 9 times 9. So 81. Write this as an exponent. Well, this is equal to 4 to the fourth power because there are 4 4's being multiplied together here. The dot is often used for multiplication as well as the cross. There's no difference between them if you're multiplying scalar values, i.e. values that don't have directions. However, when you start doing vectors, dot and cross products are very different. Write each power as a product of the same factor. 7 to the fourth power, well, that's equal to 7 times 7 times 7 times 7. 22 to the third power, oh, that's 22 times 22 times 22. 8 to the second power, or 8 squared, that's 8 by 8. 12 to the third power, that's 12 times 12 times 12. And evaluate each expression. 2 to the seventh power. 2 to the sixth power is equal to 2 to the third power, in a bracket, squared. And 2 to the third power is 8. So, this is 2 to the sixth power times 2, or 8 squared times 2. In other words, 64 times 2, or 128. Now 8 to the third power, that's equal to 2 to the ninth. Or you could go for 64 times 8, 512. Why did I go for 2 to the ninth earlier? Well, that's because 2 to the 10th is 1024, which is a number that is not that hard to remember, which means that 2 to the ninth is just half of that. Oh, well, then. Yeah, that's why. So, 7. 6 to the fourth power. You got 6, 36, 216, and then it gets irritating real quick, which is why I decided to just push a calculator button. 1296. 5 to the third power, 5, 25, 125 equals 125. Write each of these in exponential form. Well, we have how many 2's here multiplied together? We got 5 2's, so this is 2 to the fifth. And here we have 7 7's, so 7 to the seventh. 12 times 12 is 12 squared. And here we have a lot of 1's. We have 8 1's to be exact. So that's 1 to the power of 8. If you have the product of a number and itself, that's a square of the number, such as 4, 25, and 2.25. These numbers are perfect squares because they're squares of rational numbers. However, I should warn you people that usually perfect square means square of an integer. Like say 1 squared, 2 squared, 3 squared, 4 squared. These are perfect squares. Or 0 squared, which is equal to 0, which is also a perfect square. Usually, in most places, you'll find that the definition of perfect square is square of an integer. However, there are places where 2.25 is considered a perfect square because it's a square of a rational number, i.e. a number that can be represented by a fraction. It is not an infinitely long, non-repeating decimal. Yes, you can have infinitely long decimals for fractions, but they always end up repeating. That's why they are rational numbers. Now, the factors multiplied together to form perfect squares are called square roots. You have a positive and negative square root. However, in North America, the square root sign, or the radical sign, is used to indicate the positive square root of a number. That's why root of 25 is equal to 5 in North America. In Asia, I remember the convention being plus minus 5. And in some other places too. Because it's true. The square root of 36, i.e. the numbers that square to say 36, are plus minus 6. By North American convention though, that's just 6. Find the square of 4. Well, 4 squared is equal to 16. Find root of 144. Well, that's 12. A square tile has an area of 196 square inches. What are the dimensions of the tile? It's a square tile, so the area is the side length squared. S squared is equal to 196. S is equal to 14 inches. So S is tile side length. Exercises. Find the square of each number. 3 squared is equal to 9. 8 squared is equal to 8 by 8 is 64. 11 squared is 121. Although your times tables, you usually only bother going up to 9 times 9, because going up beyond that is stuff you can just whip out long multiplication for. For squares, people usually stop at somewhere around 15 squared is pretty typical. Sometimes you also bother with 16 squared, which is 256, just because that's kind of relevant in, say, computer science. 17 squared, 289. People don't usually try on purpose to memorize the squares past 15 squared. But you sometimes just pick things up. And you also get stuff like 20 squared. Whoa, so complicated. No. So, yeah, it's obviously 400. So, and then you have stuff like 25 squared. Yeah, that's 625. Like, it's powers of 5 stuff is not that bad. At least at that point. So, let's find each of these square roots. Root of 16, that's equal to 4, because 4 times 4 is 16. Root of 49, oh, we know 7 times 7 is 49. 289, well, this is 17. So, 1024. Hey, guys, what did we say earlier about computer science? 1024 the square root is 32. 361, well, if you need to use a calculator, use one, but you notice something important about this number. It's 400 minus 20 minus 19. So in other words, 20 by 20 minus 20 brings you down to 19 by 20. And then you get rid of another 19, which brings you down to 19 by 19. 19, 121, square rooted is 11. Order of operations. I remember this as being BEDMAS, which is brackets, exponents, division, multiplication, and then addition, subtraction. So you do all the operations within brackets first, with the innermost bracket taking priority. You evaluate all powers before other operations after the brackets. Because, like if you say have a x to the third power, and then you substitute something for x, what you actually are doing is this. So really an exponent is another form of bracket, except it denotes that it also multiplies it by itself a bunch of times. Multiply and divide in order from left to right, and then you add and subtract in order from left to right. These are the orders of operations. For example, let's evaluate 11 plus 2 in brackets minus 5 times 2. Well, 11 plus 2 is 13. We could write minus 5 times 2 if we were particularly picky about this. But notice that this multiplication is separated from this bracket by a lower priority operator, the subtraction. That's why it's legitimate to just do them separately. Otherwise, if you have like 2 stacks or 3 stacks of plus nested brackets, you would end up doing a lot of steps if you didn't do them in parallel. So this gives you 3. Evaluate this thing. 8 plus 8 squared divided by 4. So that's looking at 8 plus 16. Which leaves us with 24. Okay then. Let's evaluate these expressions. 1 plus 6 times 3. Well, this is equal to 7 times 3, which is equal to 21. 29 minus 3 times 8. Well, the 3 times 8 has priority because division and multiplication come before addition and subtraction. So this is 29 minus 24, which is equal to 5. 7 plus 5 times 3, well, that's 7 plus 15, which leaves us with 22. 42 divided by 6 minus 8 plus 2. 42 divided by 6 leaves us with 7. The brackets here were completely unnecessary because division has priority over subtraction and addition. 7 minus 8 plus 2. This would give us negative 1 plus 2, which gives us 1. Now for 35 divided by 7 times 2, we end up with 5 times 2, which is equal to 10. 2.5 times 10 to the third, well, that's 2.5 times 1,000, which is equal to 2,500. 45 divided by 9 plus 36 divided by 9. 45 divided by 9 leaves us with 5. And then 36 divided by 9 is 4. So that's a 9. 42 divided by 6 times 2 minus 9. Well, we start with 42 divided by 6, which leaves us with 7. Times 2 minus 9. 14 minus 9, which is equal to 5. Now, for 2 times 7 minus 3 squared plus 2, we know that exponents have priority over division and multiplication, but there's a lower priority in between. That means we can process them in parallel. 2 times 7 is 14, minus 9 plus 2. Otherwise, we would just end up with another line that says 2 times 7 minus 9 plus 2. Yeah, no, I don't think any of us are particularly interested in that. So 14 minus 9 leaves us with 5 plus 2 is 7. 3 times 2 squared plus 32 divided by 8. Notice the lower priority addition in between these two. That means we can do 3 times 4 plus 4. Otherwise, well, we would have ended up with this thing right here, and then we would simplify both in the next step. Or, yes, we could do one at a time, but it wouldn't make no difference because of the lower priority operator in the middle. 3 times 4 is 12, plus 4 is equal to 16. 3 times 6 minus 9 minus 8 cubed. So there is a low priority operator in the middle. 18 minus 1 to the third. So 18 minus 1, which is equal to 17. 3.5 times 10 squared, well, that's equal to 3.5 times 100, which is equal to 350. I hope everyone's brushed up on their order of operations. Based on the information in the problem, if you don't have an idea of how to work this out mathematically, you can initially take a few stabs in the dark and see if you have a idea that comes to mind. Like, for example, it's the same old explore, plan, solve, and check strategy, except we kind of emphasize this part. Estimate the solution. For example, if you have a person who saw 40 birds and cats in one day and saw a total of 110 legs, birds have 2 legs, cats have 4. How many of each type of animal did Dr. Miller see in one day? Well, if you aren't sure how to do this problem, you can go, okay, so let's say he saw 20 birds and 20 cats. That would leave us with how many legs? It would leave us with 40 plus 80, which is 120 legs. Like say, 20 birds plus 20 cats is equal to 120 legs. Obviously we need more birds and less cats. So let's try adjusting this until we have the right number. For every cat we turn into a bird, well, every hypothetical cat that we turn into a hypothetical bird, because we're not doing transformations of animals here. That's magic. No. Or you're waiting a very long time for evolution to produce something that remotely fits the common definition of bird or cat. Let's not think too far about that. So, what happens if you take one of these hypothetical cats and convert it to a hypothetical bird? You lose 2 legs. So 10 legs loss needed. Minus 1c plus 1b gives minus 2 legs. Okay? Notice I'm abbreviating a lot. So we need minus 10 legs. Therefore, minus 5c plus 5b gives minus 10 legs. So, we need 25 birds and 15 cats for 110 legs. Yeah. So, we made an estimate, and then we refined the estimate. And in the end, we got the correct answer. So we guessed, and then we checked on how to get it to be more correct, and we got there eventually. I do not recommend this method unless you have absolutely no idea how you're going to get at a problem. So, in a math class of 26 students, each girl drew a triangle and each boy drew a square. If there were 89 sides in all, how many girls and how many boys were in the class? Look, you can guess and check this. I do not recommend it because you could use algebra. G girls, B boys, G plus B is equal to 26 total students. And 3 sides per girl plus 4 sides per boy is equal to 89. 1 and 2. 2 minus 3 times 1 would be, well, we got rid of the girls because we subtracted 3G. 4B minus 3B leaves us with B, which is equal to 89 minus 3 times 26. What's 3 times 25? 3 times 25 is 75. So 3 times 26 must be 3 more than that. So 89 minus 78, which is equal to 11. And therefore, so G is equal to, from 1, like you should really write substitute back into a number 1, but here we're just skipping a few steps. The number of girls plus 11 is equal to 26, therefore there are 15 girls. Alright, algebra, variables and expressions. To evaluate an algebraic expression, you replace each variable with its numerical value. We call this substitution. Then you use the order of operations to simplify. For example, do you notice something here? When you substitute in, you should use bracket multiplication instead of dot or cross product. This makes your substitution more distinguishable, generally. And then you just simplify. 8 by 8 is 64, and then minus 7, well, it's 57. Evaluate 6m minus 2n if m equals 6 and n equals 5. Well, use the brackets when you substitute in. And you get 36 minus 10, so 26. Okay, evaluate 1/3 AB if A equals 7 and B equals 6. Well, that's equal to 1/3 times 7 times 6. So we can cancel and we get 2. So 2 times 7 is 14. Now let's evaluate x to the third power plus 4 if x is equal to 3. That means 3 to the third power plus 4, which is 3 times 9 is 27, plus 4, and that's 31. Okay, let's do some exercises. Evaluate each expression if a equals 4, b equals 2, and c equals 7. 2ac. Well, 2ac is just substitute in. A equals 4, and c equals 7. So 2 times 4 is 8. 7 times 8 is 56. C minus a times b to the fourth power. That's 7 minus 4. Then times b to the fourth power. B is 2 to the fourth power. So 7 minus 4 is 3 times 2 to the fourth power, which is 2 times 2 is 4. 4 times 4, or rather, 4 times 2 is 8. 8 times 2 is 16 if you haven't done nested exponents yet. But it's 16. I just realized that you guys might not have done nested exponents yet. 3 times 16 is 48. So A, B, C. Well, if A equals 4, B equals 2, and C equals 7, this is 4 times 2 times 7. And you can do all your multiplying and dividing in one step. Which means you're looking at 4 times 2, which is 8. And then times 7, so 56. AB over 6, well, that's 4 times 2 over 6, which leaves us with, well, we cancel. And this ends up being 4 over 3. Equations. An equation is a sentence in mathematics that contains an equal sign. It tells you that the left side is equal to the right side. The solution of an equation is the value that when you substitute in makes the equation true, i.e., when you put those values in, left side actually does equal right side. For example, solve 22 plus y equals 31 mentally. Well, 22 plus something equals 31. That something is equal to 31 minus 22. Well, 31 minus 21 is 10. And then minus 1 again. Oh, that's 9. Or you can go, well, 22 plus 10 is equal to 32. So 1 less than that is 9. On their annual family vacation, the Whites travel 790 miles in 2 days. If on the first day they travel 490 miles, how many miles must they drive on the second day to reach their destination? This tells us that let second day travel be X miles. This tells us that x, well, actually it should be 490 plus x, because usually when you're talking about adding up the amount traveled, you add them up in order, right? Like it's intuitive. So it's 490 plus x, could have written x plus 490, but whatever, is equal to 790. X is equal to 790 minus 490, which is 300. Or, well, you could have just looked at the addition and gone, yeah, it's got to be 300. Because 4 plus 3 equals 7. And none of the other digits change. So, is there a problem here? Well, according to GRASP, the last step would be present. Now, no, we're not going to actually write a statement here, but really we should at least put the units. Even in the explore, plan, solve, check method, you have solve, which includes units, because units are slightly important to your answer. How far did they travel? 300. 300 what? Paces? Feet? Which are shorter than paces, by the way. Kilometers? Leagues? Well, units are important business. Oh, yeah. If you're going to present, you basically rewrite the last bit of the question as a statement instead of a question. So, they must drive 300 miles on the second day would be your statement here. Exercises. Solve each solution mentally. So no calculators, guys. Well, k plus 9 is equal to 15. K is, we know that 6 plus 9 is 15. Or 15 minus 9 is 6. So k is equal to 6. G minus 15 is equal to 20. So G is 20 plus 15, 35. 4y is equal to 24. Therefore, y is equal to 6. Because divide 24 by 4. And you get 6. A over 5 is equal to 9. Well, A equals 9 times 5, then 45. X over 6 is equal to 5. X is equal to 30. H plus 2R is equal to 24. Well, we know that 2R is equal to 24 minus 8, which is 16. R is equal to 8. 12 times 9 is equal to H. 2 times 9 is 18. 1 times 9 is 9, so H is equal to 108. N divided by 13 is equal to 8. N is equal to 13 times 8. Now we know that 12.5 times 8 is equal to 100. So we got half of 8 on top of that, which is 104 then. Or you could have gone long multiplication and gone 3 by 8 is 24. 1 by 8 is 8. Yeah. So define a variable and then write and solve an equation. Brett wants to buy a video game. It costs $17.15. He has $15 saved from his weekly allowance. How much money does he need to borrow from his mother in order to buy the game? Well, X dollars. You can write borrowed X dollars, or he borrows X dollars, or he needs to borrow X dollars. But the point is that 15.00 plus X is equal to 17.50. X is equal to 2.50 dollars. Technically speaking, this makes no sense. Why? He borrowed $2.50 dollars. Yeah, but honestly, nobody cares. Yeah, because it's immediately obvious what the answer is supposed to say. And you can put a statement. He needs to borrow $2.50. You know what I think? I think he needs to borrow $0, and he needs to wait for the next time the game goes on sale, or wait until his allowance builds up if this is the full price of the game. Unless he's buying a game in pre-order, which is usually not the most brilliant idea known to man, so try to avoid that. Unless there are some nifty perks involved. algebra properties. The distributive property means that if you multiply a bracket, you multiply every item inside that bracket by whatever you're multiplying the bracket with. So A times B plus C is equal to A times B plus A times C. Minus, same thing. A times B minus A times C, if this was A times B minus C. Or you could say plus A times negative C. The commutative property is during addition or multiplication, the order does not matter. If you say have A times B, it's the same as B times A. If you have A plus B, it's the same as B plus A. Division and subtraction do not have this characteristic because obviously 10 minus 5 is not equal to 5 minus 10. Okay? So they're not exchangeable. The associative property of addition means that when you add things together, the order you add them in does not matter. For multiplication, when you multiply things together, the order you multiply them in does not matter. Identity property of addition is that if you add 0 to something, it stays the same. For multiplication, the identity property is when you times 1, it stays the same. Let's use the distributive property to write 6 times 4 plus 3 as an equivalent expression. Then evaluate the expression. So, it's equal to 6 times 4 plus 6 times 3. So 24 plus 18, which leaves us with 42. Use both the commutative and associative properties. Associative is the order you do the things in doesn't matter, and commutative is the order you write them in don't matter for addition and multiplication. To write an equivalent expression to 3 plus 2 plus 6. Well then, if we use the associative property, we'd be looking at 3 plus 2 plus 6. But commutative, that changes it to 2 plus 3 plus 6. Now let's use the distributive property to write each of these expressions as an equivalent expression and then evaluate. 3 times 7 plus 2 is 3 times 7 plus 3 times 2, which leaves us with 21 plus 6, or 27. 4 times 8 plus 7 is 4 times 8 plus 4 times 7. 32 plus 28, which is 60. Although in this case, I would not recommend breaking it up before solving. Why? 8 plus 7 is 15. 4 times 15 is really convenient. And also here, really, you don't use distributive property that much when doing math like this with no variables involved. Usually it's not really worth the hassle. So 2 times 3 plus 4, 2 times 7, come on, it's not that bad. But because we're supposed to use distributive property, we will. 2 times 3 plus 2 times 4, which is 6, plus 8, which is equal to 14. Name the property shown by each statement here. 9 times 1 is equal to 9. This is the identity. property. Specifically, it's the one for multiplication. Now, 7 times 4 is equal to 4 times 7. This is the commutative property, in which the order you write them in when you multiply two things together can be flipped around. The associative one is the order you do them in can be different. Commutative, it's multiplication. And 7 plus 6 plus 2 equals 7 plus, 6 plus 2. That is associative. Depending on where you live, you may have to specify that it's the associative property of addition, or you may not, because associative is specific to addition and multiplication. And, well, okay, commutative is too. So in some places you wouldn't even have to specify this part. Here, 6 times 5 plus 2 is equal to 6 times 5 plus 6 times 2. That's the distributive property. Distributive property. 10 plus 11 and 11 plus 10. This is commutative. And it's addition. 1 times 30 is equal to 30. Well, this is the identity property of multiplication. Multiplication. Seven times 5 times 3 is equal to 7 times 5 times 3 is associative. Associative. And it's multiplication. Multiplication. 3 is equal to 0 plus 3. This is identity expression, or identity property of addition. Add 0 and it stays the same. That's what the identity property of addition is. Arithmetic sequences are lists where each item is found by adding the same number to the previous item. So what do we call these items? We call these items terms. And we have term 1, term 2, term 3, and so on. And we have a hypothetical term 0. One, 2, 3, 4, 5 is an arithmetic sequence because you add 1 each time. Now describe the relationship between terms in the arithmetic sequence 21, 27, 33, 39. Oh, it's plus 6. Plus 6 again. And then plus 6 again. Actually, we should write this over here. Plus 6 again. Then write the next 3 terms in the sequence. The next 3 terms are 39 plus 6, which is 45, plus 6 again, which leaves us with 51, and plus 6 again, which gives us 57. Example 2. Brian's parents have started giving him a monthly allowance for 1 year. Each month they will increase his allowance by $10. Suppose this pattern continues. What algebraic expression can be used to find Brian's allowance after any given number of months? Because the first month he gets $10, and for each month thereafter his allowance is increased by $10. Notice here, it doesn't seem to have stated the initial term, right? Actually, they decided to start giving him a monthly allowance, which means they started before with 0 allowance. So the first month, his allowance has increased by $10 from 0. Therefore, the allowance in month X is 10X. So, for X equals 10, term 10 is equal to $100 in the 10th month. Right? Well, that depends on how your allowance works. For example, if your allowance increases by $10 a month, there are 2 possible meanings. One is the amount of money you get each month increases by $10. The other is that you get $10 a month. So yeah, how much he receives for allowance depends on whether this is a trick question. But it's probably supposed to be $100. Now, let's do some exercises. Describe the relationship between terms in the arithmetic sequences. Write the next 3 terms in the sequence. Well, this one, we can see that each term increases by 2. Term n is equal to term n minus 1 plus 2. And it's also equal to just 2n if you want a general term. The general term is term n equals 2n. So the next 3 terms, 10, 12, 14. 1, 4, 7, 10. Yeah, term n is equal to term n minus 1, so the previous term, plus 3. It's also equal to 3n minus 2 to give us the correct T1 and every term thereafter. So, next terms, 13, 16, 19. 0.4, 0.8, 1.2, 1.6. Term n is equal to term n minus 1 plus 0.4. Or, for a general term, you would have term n is equal to 0.4n. So, the next terms would be 2.0, 2.4, 2.8. Now here, 100, 113, 126. Well, we have fewer reference points, but we're told this is an arithmetic sequence. That means even if we only had 2 numbers, 2 adjacent terms, or even just 2 terms where we know their term numbers, we can figure out what the interval between terms is. This is term n is equal to term n minus 1 plus 13, and it's equal to 13n plus 100 minus 13 is 87. So the next one is 139, and the next term after that is 13 plus 39. Well, 139, but the 1 goes in front. 13 plus 39 gives us 52. And then plus 13 again, which is 165. So 1.5, 2.0, 2.5, it's pretty obvious that it's increasing by 0.5 each time. Term n is equal to term n minus 1 plus 0.5. And the general term would be 0.5 n plus 1. So you get 3.0, 3.5, 4.0. Now 10, 19, 28, well, it's the previous term plus 9. And the general term would be 9n plus 1. So 28 plus 9 gives us 37. Then it's 46. Then it's 55. Now, let's say it's February, and a bakery that just opened currently only sells 2 types of bread. And each month, the bakery will add 2 more types of bread to their menu. Suppose this pattern continues. What algebraic expression can be used to find the number of bread types offered after any given number of months? In the nth month of operation, you have 2n bread types. And in January of next year, that's the 12th month. So 24 breads are expected to be offered. Yeah, let's write offered here. Equations and functions in algebra. If you have 2 variables, then the solution consists of 2 numbers. 1 for each variable that makes the equation true. When a relationship has exactly 1 output value for each input value, it is called a function. Function tables help organize your input numbers, your output numbers, and function rules. Complete a function table for y equals 5x, then state the domain and range of your function table and of the function itself. So, x, 5x, and y is your usual format for this sort of thing at the beginning. And then you get rid of the middle column because y is the same. So you have, say, x equals 0, 5x equals 0, y equals 0, x equals 1, 5x equals 5, and y would be equal to 5x, which is 5. And 2, 10, and 10. As you can see, the 5x column is pretty redundant. As long as you have the relationship stated above the table somewhere, or you go y equals 5x. Yeah. So, domain of this function table are the x values we used. 0, 1, 2. Because we're using x as the independent variable. Like if you're expressing one variable in terms of another, here you would be expressing 5x in terms of y. No, you don't do that. You express x in terms of y. Or you express y in terms of x. Like say 1y is equal to 5x. Of course, if it was y equals x, then which one's the independent variable, your input number, which you use for the domain, and which one's for the range? Doesn't really matter, does it? So domain is 0, 1, 2 because those are the x values we used. Range is, now this is for the table, by the way, so it's table domain and range. Range is 0, 5, and 10. However, the function's domain is, wait a second, what values of x exist where this equation can possibly be true? Like, are there any values of x where there is no corresponding value of y? No. So it's x is all real numbers. X is an element of the real numbers. And the range, well, are there any y values, so the range values that are impossible? No. You go from negative infinity to positive infinity. Y is an element of the real numbers. Now, let's complete the following function tables and state the domain and range of the function tables. For y equals x plus 3, I took the liberty of omitting the, say, x plus 3 or whatever the intermediate column is that you may have to do at the beginning of you doing functions. So, x equals 0, y is x plus 3, so 3. 1 plus 3 is 4, 2 plus 3 is 5, 3 plus 3 is 6. So, domain is x is an element of, this is like formal language. You could just say the domain was blah, blah, blah for your number set. But in more formal language, you should probably put x is an element of 0, 1, 2, and 3, this set. And range is y is an element of 3, 4, 5, and 6 in a set. Now for y equals 5x, you would have 0, 5, 10, 15. The domain is x is an element of 0, 1, 2, 3. Now range is y is an element of the set 0, 5, 10, 15. For y equals x minus 1, you would have x equals 2, y would be 2 minus 1, which is 1. X equals 3, y is 3 minus 1, which is 2. 4, 3, 5 minus 1 is 4. So the domain here is the x values you used in the table if you're asked for the table's domain. You don't look at the function itself and go, are there any x values where we don't have a y value? And is there any y value that is impossible to obtain? Yeah, you don't do that for domain and range unless you ask for the function's domain and range. If you ask for the function table that you made and its domain and range, you just use the values you actually used. Okay? Because at the current stage, pretty much all of your functions that, actually, I don't think you do rational functions until pretty late. So for a lot of them, you're going to get domain is just all real numbers. Because for all values of x, you can get a y value. Like, I think it's pretty late that you do, say, 1 over x, where you can't have x equals 0. That gives you undefined, or things like that. For y, the values you actually saw in the table were 1, 2, 3, 4. That was the range you had for the table. For all of these, because they are linear functions, they can be graphed as straight lines, and they aren't vertical or horizontal, you're going to end up with the domain and range are all real numbers. Because for any real number range value, any real number y value, you can find a domain value where it shows up. And for any real number x value, you can find a y value. So that's it for now. And just remember that your function table's domain and range is very different from the function itself's domain and range. The domain is the possible input numbers or independent variables, which usually we use x for and plot along the horizontal axis of a graph, where the function has some value, specifically one value, because that's what makes it a function instead of just a relation. Your output numbers, all the possible output numbers put together, are your function's range. So all the dependent variables, all the output numbers. The function rules, well, that's the equation associating the output number with the input number, or vice versa, actually. So, the independent variable is along your horizontal axis, and usually we use x, and the dependent variable is usually y, and it's usually the vertical axis. Okay? So that's it for this chapter. We'll see each other again next chapter.